Hello everyone, my name is Sean Lacey of Lacey Maths and Stats Consultancy, and this video is an example of how to present multiple linear regression analysis results in RStudio. I have a video up on YouTube already which is looking at presenting simple linear regression analysis results in RStudio, and this is, I suppose, the next level after that the difference between simple linear regression and multiple linear regression is down to the number of predictors or explanatory variables that you have, where in simple linear regression, which is demonstrating this video already up on YouTube, is where you have one explanatory variable or one predictor variable, whichever you want to call it, while the video that we're actually doing here at the moment is where there's going to be more than one explanatory or predictor variable. So I suppose just kind of give an idea of what we're kind of working towards is I'm going to look at where there's this sample data of where there's one response measurement, 5 predictors. I'm going to just say call them predictors now as opposed to continuously chopping and changing between explanatory and predictor. So we're going to have 5 predictor variables, and when we run off the analysis the first time, there's going to be an issue with one of them, mainly that it is going to be causing a multicollinearity. So then we remove that, and then we end up with a model that we're somewhere kind of happy with. And then it's a case of when we have this model that we're happy with, and then we check it for satisfying the conditions of normality around the residuals and variation with the residuals, that we might look at presenting the model in a table, and then this is a suggestion to how we might present the model. Okay, and you can see here that with this set, I suppose it's just having a picture in your mind, and then this kind of gives you kind of a target to what to work towards in RStudio. So it's a case of, in here we're going to be looking at setting up a couple of vectors. So a vector with all the labels, a vector with our R-squared statistic with the regression coefficients, another vector for the lower regression coefficients for the confidence interval, upper regression coefficients, standardized regression coefficients, and then the p-values. So we're going to have these vectors, and this is, I suppose, it's just a nice way that I find that is well received when I'm presenting multiple linear regression analysis results. Okay, so if you come to RStudio here, what I have is I'm just going to look at where there are 10, I suppose, 10 complete sets of data. I'm given, there's no real context to this. This is all just very kind of general terms of where there's a response measurement. There are 5 predictors, that's what I'm saying here. Then I put them as data frame, calling them DF, and then I suppose just for the purposes of the video, it's just nice to kind of get a visual to what I suppose the data looks like when it's graphed. So I'm just going to highlight all that, put this together, and we'll end up with these 5 scatter plots. Here we go. Okay, so this is what we have here. So what we can see is predictor 1 seems to be kind of a nice positive linear relationship between predictor 1 and the response variable. Predictor 2 seems to be good linear relationship, so does predictor 3. Predictor 4 seems to be a negative linear relationship anyway, appears, and it doesn't seem to be overly good. And predictor 5 doesn't seem to have a great relationship. It seems to be marginally positive, but overall it doesn't seem to be actually a great linear relationship at all, right? You'd nearly say that this line that is fitting is nearly a horizontal line, okay? So it's just a case of if we're putting all these variables into our model, and then I suppose how might we end up presenting a model at the very end, okay? So here we go, back here to the script. So the first thing is going to look at running off the full model, which I'm going to call model F. I'm going to call it fit1. And when I run this off, you can then see that there's a kind of, it does seem a bit strange. Now I've already mentioned that there's going to be multicollinearity, and I suppose a way of kind of flagging if you have multicollinearity is where you have a very high adjusted R-squared. So we can kind of see that down here. There is a very high adjusted R-squared, but also I think to kind of flag whether or not there's multicollinearity is your regression coefficients, are they going in the opposite direction to what you'd expect? So if you think to our plot that we actually had, I've actually closed it already, but if you look at, actually I'll just run it off there a second just so you can kind of see with the lines. If you look at predictor 1 here, you can see predictor 1, there is quite a good positive linear relationship with predictor 1, but yet when we look at the model here, when we ran it off as a full model, you can see, look, that the regression coefficient is pretty much 0. And it is statistically insignificant. So that's going to kind of give a guideline to the fact that there could be multicollinearity in the model. There's various ways of obviously exploring whether multicollinearity is present. For the purposes of this video, I'm just going to use the variance inflation factor. So from the faraway library, I'm going to run that off and end up with this result. And what we can see here is that predictor 1 is definitely causing multicollinearity here. Okay, so there's an issue with predictor 1, so in order for the model to be accurate, we need to remove a variable that is causing multicollinearity. So we're going to look at removing predictor 1 now. So I would generally approach that you remove one variable at a time as opposed to moving a couple together, because when you remove one, then you get a better picture of what's happening with the other ones. Okay, so I'm going to look at moving predictor 1, and I'm going to just highlight that and run off the variance inflation factor. When I run off the model for predictor 1, what I can see here is now I'm kind of getting much nicer results for my predictors 2, 3, 4, 5. 3 of them are significant. Predictor 5 is actually insignificant. It's not contributing. You can see the adjusted R squared actually improved nicely. When I look at the variance inflation factor, they're actually all individually, they're all actually they're fine. There's no issues. So we seem to have removed the variable that was causing multicollinearity in the model. And I'm going to actually stop here now at this point for this one. And now people might argue that we should look at removing predictor 5. I suppose I would find that a grey area. It all depends on what you're actually measuring. Just removing variables because they're insignificant, is that really reflective of what you're actually measuring? Like, is the variable that you're removing does it actually have an impact on what you're measuring in real life? And if it does, then you'd be probably maybe better off just actually leaving it in. Okay, so I mean, for me, when I try to look, I suppose, doing multiple linear regression, I do remove variables that are causing multicollinearity. Obviously, you need to do that. But if a variable is insignificant, it varies depending on to whether I remove it or leave it in, because it would all depend on what I'm actually going to be measuring. Okay, so I didn't want to necessarily be putting up a video on YouTube where I'd be kind of promoting, oh, you remove insignificant variables, because it's not always that clear cut. So I'm actually going to leave it here, as in I'm going to actually leave the predictor 5 in, because I feel it's a safer option. But in some research areas, they would remove all statistically insignificant results, and that's fine as well. I suppose it depends on the context. Okay, I would generally look at the idea that if the measurement is actually going to be there in reality, in the actual context, then if you remove it, are you actually setting up a scenario that is actually repeatable in real life? Okay, so it's obviously there can be a lot of debate and research about how you'd handle it, but for this video I felt it might be just a bit misleading, removing an insignificant variable, so I'm actually going to leave it in here. Okay, so what we can see here is we've developed two models. Model 1 had multicollinearity, model 2 has no issues with multicollinearity, and I'm going to proceed with that. Okay, I'm going to do a video later on where I'm going to look at maybe how we can maybe, I suppose, present our model selection, as in the process in our model selection. That will be another video I'm going to look at doing. The purposes of this video is basically we have this model, how do we present it? Okay, how do we kind of format it in RStudio that it will and then write it to Excel that it will be some way a nice table. That's what I want to look at here. What you would in practice be doing next, but it's just not the focus of this video, is you have a model, we're going to be calling it fit2. You would then check the residuals of that model to make sure that the residuals are satisfying the assumptions of normality and the variation of the residuals, that there is variation among the residuals, that there is no, I suppose that the variation in the residuals is random, that there is no actual pattern. Okay, now that's just not the focus of this video, but that's obviously the step that is obviously very, very important for you to do before you actually go off and proceed to actually presenting a model. The other thing then that it will be important is if you're imagining comparing your coefficients against each other, then if your coefficients are of different units, as in if your not your coefficients, sorry, but if your predictors are of different units, then it would be important to work out the standardized regression coefficients. So what I'm just using here is this quantSci package to do this, to work out the standardized regression coefficients. So these are the standardized regression coefficients for model 1. We don't really need them. I actually didn't even output them. For model 2, though, here are our 4 standardized regression coefficients. Okay, and they will be a good, I suppose, output, good, I suppose, statistics to present in a table to complement your regression coefficients, especially if the units to your regression coefficients are different. Then you'd obviously want to be very cautious if you're thinking of comparing them, that if you plan on comparing your regression coefficients, then you'll be best standardizing them and then using them for your comparisons. Okay, so that's what that line 40 is looking at. And now the next thing is just putting all the information together. I feel that when I was putting, I suppose, getting the script together for the table, it's to have an idea in your head to what the table you want to look at. So I'm just going to kind of be chopping and changing between I suppose this is the table I'm aiming for, and how do I kind of get the script. So my first thing is to create a vector or variable called labels, which actually has these kind of 6 parts to it, okay? Overall, intercept, and the four predictors. So that's what I'm looking at doing here. So labels, there are my labels, and then the next thing I'm going to look at doing is I'm looking at my summary to fit to, and I'm going to call that output, okay? Just to give that a name, because I want to reference different parts of it. Now, what do I want to reference? I'd like to kind of get the 4 regression coefficients. I'd like to extract them out. I'd like to extract the 4 corresponding p-values. What else do I want? I want to get the adjusted R-squared. That would be something that I'm interested in. I'd also like to extract the overall p-value. That's something that I'd like as well out, okay? So there's going to be different bits of information I want to get out of this output, okay? So if I take it in stages, the first thing I'm going to look at is R-squared. Now, when I say take it in stages, I'm just kind of progressing across this from left to right. So we've looked at the tables. Now it's to look at the R-squared. So here I create, I'm looking at this, I suppose, the output, and then I'm referencing the adjusted R-squared part to it. That's what I'm doing here. Then I'm converting it to a percentage. I'm multiplying it by 1, putting it as 1 decimal place, and kind of pasting on or concatenating a percentage symbol onto it. And then so you can see I'm getting the 99.1%, and then I want to create it as a vector. So I know that the structure is that I'd have kind of 6 parts to my vector. So the first part is going to be my R-squared, or the adjusted R-squared, and then the remaining 5 parts are basically all going to be blank, empty cells. That's what I'm looking at doing here, okay? Then the next thing then will be my regression coefficients. So for the regression coefficients, if I go back to the table here, you can see I'm going to have a blank first because there's no regression coefficient to kind of match the adjusted R-squared. But I should have then my 5 regression coefficients, 1 for the intercept, and then the 4 remaining predictor variables. So that's what's next here. And that's so you can just see, look, that's why I have a blank. And then I'm looking at my regression coefficients from the model fit to, and I'm rounding it to 2 decimal places. And so that's what I'm getting here. Then what's next? What's next then is if I come here, I can see that I'm looking at my composite interval of the regression coefficient. So I have 2 blanks. And then it's looking at the composite interval for the lower, and then the composite interval for the upper. Okay, so that's what I'm doing next. So you can just see here, I'm creating 2 blank cells, and then I'm looking at the composite interval for my fit to, where I'm saying 95% composite interval. I'm ignoring the intercept part. I don't want it to output the intercept, so I'm saying ignoring the first part. Actually, what I'll do here, just so we can kind of see it, I'll just output this first. So this is the information that we have. Okay, so if I just look at conf int of the fit model to level 0.95, I end up with this. I don't want the first row, so I'm kind of removing the first row, so that's why there is a -1. And what I want then is what's left in the first column. So the first column then will give me the lower confidence interval. So if I just output that there a second, just so we can kind of see the logic to it, you can see that they're the lower limits to the confidence interval for the regression coefficients. Then I'm rounding them to 2 decimal places. Then I'll repeat the process for the upper. Okay, so I'm ignoring the first row because I'm not interested in the intercept. I obviously need the intercept, but I'm not interested in the regression coefficients around it, or whether or not or the p-value. So I ignore that, and then I'm just focusing on the other one. What's next then is the standardized regression coefficients. So again, this is where you'd have the picture in your mind. The standardized regression coefficients, there's nothing for the first 2, so we'd have 2 kind of blank cells, and then we'd have our 4 standardized regression coefficients. So that's what's next. So that's what I'm just doing here. And so obviously I've already worked out the standardized regression coefficient SRS2. That's what I had worked out here when I looked at running off the script at the start. Okay. What's next then is the p-values. Okay, so what I like to try to do is I'd like to try to have a p-value of the overall model first. Okay, that's what I wanted to do. So I came across a nice script on Stack Overflow. I'm leaving the link in there if anyone wants to see it, but it's kind of showing you how to pull out the p-value for your regression model. So the user there kind of creates this function, this LMP function of extracting that. Okay, so that's what the function will do. And then I'm looking at to extract the p-value. Then if the p-value is less than 0.005, then state it as less than 0.005. Otherwise, state what the exact p-value is. Okay, so I don't like when you present p-values that if we present it in scientific notation, I don't like that. I don't like p-values being stated as 0. I would generally state what a p-value is if I have the value. But then if it's a very small value, I would state it as being less than 0.005. And that's what this is doing. So I found that was quite a nice function, a bit of script to come across on Stack Overflow. So I have that done here, so you can just see now that that's giving me back a symbol that's less than 0.005, just to kind of show you, actually, maybe just to refresh. If I run off the summary of the fit model 2, like it's basically this p-value, that's the one I'm looking at extracting. You can see that it's presented in scientific notation here because it's so small, and I'm just looking at extracting it, having script to extract it as opposed to me typing out myself manually and then giving it a name and I'm calling it p. Then I want to look at the individual p-values, so the p-values here, these 4 p-values for each of my regression coefficients. So that's what I'm just, the first one's obviously going to be, so if I'm looking at the vector, I have this at the start, then I have a blank, and then I have my 4 remaining individual p-values. That's what I'm looking at here. So I'm saying p, blank cell, and then I'm looking at my coefficients for my 4 p-values. Okay, so if I look at output $, this here, it's just gonna, if I just do this bit here, it's just outputting the 4 p-values. That's what I want. And then I'm just saying if each p-value is less than 0.05, then state it is less than 0.0005. Sorry, I'm dropping zeros when I'm saying it so fast. And then or else state the exact p-value. So that's what I'm looking at doing here. And then I pull all the bits to put together for the data frame. Okay, so I'm just going to highlight it all again there because I mightn't have actually been running some of the lines of script with all my talking going on. So I'm just going to highlight it, going to run it, and here's my lovely data frame. Okay, so I have a data frame then with the labels that I want with my adjusted R squared, my regression coefficients, the 95% confidence interval, lower and upper, standardized regression coefficients, and then the p-values. And then the next step then is to extract that, or to write that then to Excel. And that's where this next line of code is here. I'm just going to write it to Excel, and I'm going to call it table MLR for multiple linear regression. It seems to work out okay here. So table SLR, that was from the previous video. So I'm looking at this one here. If I open up that, perfect, here I go. And then it's just a small bit of formatting left. So I'll zoom in on this. Now people have their own kind of way of doing this, and it's not that I'm saying, oh, you have to do this, but I suppose I'm just going to try to set it up the same way that I have it here on this slide here. Okay, so everyone will have the kind of their own style to doing this. I suppose what I just like with all this is basically we're not going to be creating a table where we're going to be typing in the numbers. We've basically created a table in RStudio, so we have the script for it. We're writing the table then to Excel, and now we will do a small bit of formatting of widening the columns, labeling the variables, the column headings and stuff like that. There's no problem with that, but we're not actually going to go at any of the numbers really, bar maybe changing the decimal places. So I'm just going to first convert them to numbers. That's what I'm going to do here. I'm going to round that to 1 decimal place. Perfect. I'm happy enough with this. So the only thing I'd be just careful here is just my decimal places. I'd like them to be consistent. You can see here that this is 0.4, and if it was to be 2 decimal places, it would be 0.40. So I just like that my decimal places would always be consistent, that if the second decimal place was 0, that it would be stated as 0. Okay, I just think that just looks well. All these p-values over here, I like them to be over to the right, to be aligned right, and then it's just going to widen that a small bit. And now I'm just going to be starting putting in the name. So adjusted, or here putting the symbol for a squared. Obviously it's adjusted R squared that we look at as opposed to the R squared by itself when we're doing multiple linear regression. Then the next thing here, this will be regression coefficients, and I look at, I'm actually going to put in another column here a second like this, because this here I'm going to put in here, what I'm going to look at doing here is I'm going to call you 95% confidence interval. Is that's what I called it here, just to kind of line it up. Actually I put in 2 lines. Okay, perfect. Just do this here. Now again, look, you might decide, look, that you're not interested in this bit, and that's fine. Okay, so if I merge them, so this is going to be 95% confidence CI of regression coefficients, like that, something like that, and I'll wrap that text. That just tidies up a small bit. This is the lower, this is the upper. I'm going to just center them. I'll merge this guy here like this and wrap the text, and I'll just widen it a fraction like that. That looks better. Here I'll do the same. I'll merge it and then wrap the text and then just widen it a fraction. Or did I widen it here? I left it. I did widen it. Okay, so just to get them very similar. And then here is something similar like this, like that. And then here, just fix this guy up here. What's this? I'm actually going to copy this guy down altogether and then change this to standardized. ANDARDI standardized regression coefficients, like that. And I'm just going to widen you a small bit there just to kind of get the word in one line. Again, people will have their own way of doing these things, okay? So something like that. And then this is the last one here for this, wrap the text, and then I'll put in maybe a hyphen in like that, okay? So I'm kind of be happy with this. I'm just going to line them all in the center just to make sure that that looks nice. I don't need this over here, so I'm going to just delete that. And then the next thing then is just, I mean, this is personal taste. If you wanted to merge and center that, that's fair enough. And then I'm going to just put that up here, and which way I want it like that, okay? And then this would be the same if I wanted to, actually here, I'd leave this one like this, merge and center, perfect, like that. And then here you can just see it's something similar. If I merge this, okay, and then I want to line that right. Actually, I lost it there, sorry. 0.1235, like that, okay? I think that's quite similar to what I have there. And the last one, then I'm going to just highlight it, format the cells, border, thick one for the outline, slightly thinner one for the inline, inside, press OK, and that is, to me, seems to be the same as that table there. Now with that little formatting at the end, kind of just gets messy, and look, that's down to, I suppose, personal taste of how you might want to do it, and everyone has their own way of doing these things. And I'd always feel that whenever I'm doing any kind of statistics, as in for building a report and all, there's always time in formatting tables and formatting the graphs. But I suppose the purpose of this video is just how do we get the numbers from RStudio into Excel, which you would then bring into Word, and that you'll have a transparency of that step. And it's just to have always kind of have that track record, have that diary for any kind of manipulation that you'd have done. I'd find is just a good thing to be to do, and to, I suppose, to use RStudio to its maximum capability in that regard. Okay, so look, that's the reason for doing this one. Is, as like I said, it was just a kind of a follow on from the previous video, which is simple linear regression, how to kind of present the results from a simple linear regression analysis, and this obviously one then is multiple linear regression analysis. I'm going to do a third video, which is just going to maybe looking at the idea of pulling the information together for your kind of a model selection. You can see kind of to get this result here, we actually had a 5 independent or 5 explanatory or predictor variables at the start. We removed one because of the multicollinearity. So what if you wanted to kind of present all kind of your model selection process in a table? So I'm just going to look at that as a third video in this kind of overall theme of kind of regression analysis results. Okay. Hope you're, as always, hope you're kind of happy with this video. Hope you find it to help. It's not that it's a case of, oh, this table here is the gold standard. I suppose mainly what I was trying to promote or encourage with this video is just how we can kind of pull the information or even extract the information from RStudio, from the different functions that we've used into RStudio to kind of present the results in a concise table. You might find that you want more information than I've presented in this table, or you might find that you want less information than I've presented in this table, and it can be just kind of maybe a starting point to kind of getting you thinking to how can you use RStudio to kind of format the tables that you're going to then present in your Word report. Okay. But like always, there's loads of ways of doing these things in in RStudio. And if you find that you have more efficient ways of doing it and you'd like to share it, then please comment below. That's more than welcome. And if you find that this video is of help, then liking and sharing it would be good. And subscribing to it is always a positive if you would like updates of when the next videos are going to come online. Okay, but I hope you find this of help, and till next time, all the best. Bye now.